questions of chapter atoms. Question 1. Choose the correct alternative from the clues given at the end of each statement. The size of the atom in Thomson's model. Okay. No difference. The atomic size in Rutherford atom model. In both the cases, it is believed that the electrostatic force between positive charges and negative charges, irrespective of the difference in the arrangements. In part B, in the ground state of Thomson's atom model, electrons are in stable equilibrium, while the electrons in Rutherford atom model experience a net force. That's the reason we need to consider the spiral path and the problem in explaining the stability of atom model, etc. Then, part C, a classical atom based on Rutherford atom model is doomed to collapse. Then, part D, an atom has a nearly continuous mass distribution in Thomson's atom model, but has highly non-uniform mass distribution in Rutherford atom model. Then part E, the positively charged part of atom possesses most of the mass in both the models. Only the difference that in Thomson's model, the positive charges are distributed, while in Rutherford model, the positive charge is concentrated in a small region. But in both the models, the majority of the mass of the atom is contributed by the positively charged parts. Then question 2. Suppose you are given a chance to repeat the alpha particle scattering experiment using a thin sheet of solid hydrogen in place of the gold foil. Okay. What results do you expect? You know, gold is a heavy metal. Okay. So comparatively large value of atomic number. So it's a heavy atom. Hydrogen is a light atom, you know, lighter than alpha particles. So when alpha particles collide with the hydrogen foil, it's not the alpha particle that's scattered, it is a hydrogen gets scattered, because hydrogen is lighter than alpha particle. So whatever the result you observed in the case of alpha particle experiment is not going to get when you use hydrogen, and the hydrogen will travel faster than alpha particle as it is having or light weight. Therefore, you cannot conduct the experiment properly, and you are not going to get the expected result also. Now, next question 3. What is the shortest wavelength present in the Paschen series of spectral lines? Shortest wavelength. Shortest wavelength means we have the maximum frequency. Okay, as we have the maximum frequency here, we have to see frequency maximum indicates the energy is maximum. Therefore, the initial level of de-excitation will be from infinity. Maximum frequency, that is maximum energy. Therefore, you can use the formula 1 by lambda is equal to R into, where lambda is equal to R into it is Paschen series. So 1 by 9 minus 1 by infinity square. And from there, the value of lambda you can calculate. Or you can use any other method in terms of energy or in terms of frequency. So you can follow suitable method and you can find the value of lambda. Then next, question 4. A difference of 2.3 electron volts separates two energy levels in an atom. What is the frequency of radiation emitted when the atom makes a transition from the upper level to the lower level. So frequency you have to calculate. So we have the formula nu is equal to E by H is equal to H nu formula you can use is equal to, you can substitute the values, only you can do here when you calculate the energy it should be converted into joule. So take care of that so that you can find the value of frequency. Then next question 5, the ground state energy of hydrogen is minus 13.6 electron volt. What are the kinetic and potential energies of the electron in this stage? You know the relation between kinetic energy, potential energy and total energy. Now total energy is given, therefore kinetic energy is the positive of total energy, that is plus 13.6 electron volt, and potential energy is double of total energy, so you will get minus, and it is negative also, minus 13.6 into 2 electron volt. Okay, now next question 6, a hydrogen atom initially in the ground level absorbs a photon which excites it to the n equal to 4 level. Determine the wavelength and frequency. Okay, so it is excited to n is equal to 4 level. So wavelength you can calculate using the equation 1 by lambda is equal to r into the final level is n is equal to 4 minus initial level is the first level. Okay, so you can calculate the value of 1 by lambda. From 1 by lambda you can find the value of lambda, and you can find the value of frequency mu also. Here there is a possibility you will get the value negative. Okay, because I actually, you know, this is a formula we obtained from energy equation. You remember that equation for the Rydberg constant derived. Then here you get the negative value because energy is absorbed. So when you find the value of lambda and mu, you can just drop that negative sign. Okay, it indicates just the absorption of energy. Then question 7, using Bose model, calculate the speed of electron in a hydrogen atom in the n equal to 1, 2 and 3 levels. Calculate the orbital period in each of these levels. Okay, the speed of electron you have to calculate. The speed of electron in the nth orbit, we have Vn is equal to E square divided by 2 epsilon naught nh. 2 epsilon naught nh. Now substitute the value n is equal to 1, then you find the value of V1. Once you get the value of V1, you know the relation between V1 and Vn. So we can have Vn is equal to V1 by n. Now substituting the values of n, you can find the value of V2. V2 is equal to V1 divided by 2, and V3 is equal to V1 divided by 3. So you can find the value of V2 and V3. Then again you are asked to calculate the orbital period in each of these levels. So orbital periods, when you calculate, again here period t is equal to the distance traveled 2 pi r n divided by Vn. I will substitute the values of Rn and Vn. Okay, then take n is equal to 1 so that you can calculate the value of T1. Find the value of T1 and value of Rn, Rn is equal to n square h square epsilon naught divided by pi m e square. So in this formula for time period, substitute the value of Rn and Vn, simplify, then substitute n is equal to 1, then find the value of T1. Once you get the value of T1, then you can find out what is the relation between Tn and T1. So you will get Tn is equal to n cube T1. N cube T1. So using this relation, you can find the values of T2 and T3. T2 and T3. Now, next, question 8. The radius of the innermost electron orbit of a hydrogen atom is 5.3 into 10 power minus 11 meter, Bohr radius. What are the radii of n equal to 2 and n equal to 3 orbits? Again, the relation we can use, we have Rn is equal to n square R1. Rn is equal to n square R1. R1 is given in the question. So you take n is equal to 2 and find the value of R2. And take n is equal to 3, then find the value of R3. So you get the answer. Then next, question 9. A 12.5 electron volt electron beam is used to bombard gaseous hydrogen at room temperature. What series of wavelengths will be emitted? Okay. So here already we know the ground state of hydrogen atom having an energy minus 13.6 electron volt. And when you bombard the hydrogen with a 12.5 electron volt electron beam, then the electron in the hydrogen atom can absorb a maximum energy of 12.5 electron volt also. So that what happens? Its total energy now becomes approximately 1.1 electron volt. An electron in hydrogen atom having energy 1.1 electron volt means its energy is almost close to n is equal to 311. That means what happens when you bombard the hydrogen atom with this electron beam? Okay, the electron in the hydrogen will be excited to third level. That means second excited level. Now, from that excited level, what happens? The electron will de-excite to the lower energy levels. What are the possibilities of de-excitement? You have the possibilities like this. First of all, we can have n is equal to 1 to n is equal to 1 to n is equal to the hydrogen is the electron is already in n is equal to 3 level. From n is equal to 3 level to n is equal to 1. That is one possibility. Next possibility, from n equal to 3 to n equal to 2. That is another possibility. Then once it reaches the second level, then again you have one more possibility, n is equal to 2 to n is equal to 1. So, three types of radiations you will get from the hydrogen atom. Okay, one is for the de-excitation from 30 to 1, next for the de-excitation from 30 to 2, and then the last one is for the de-excitation from second to first level. So accordingly, you can see here you will get a spectral line of Lyman series. Here again you get a spectral line of Lyman series, and here you will get a spectral line of Balmer series. So these are the possibilities. Now in each case, okay, the question what series of wavelengths will be emitted, you can calculate the wavelengths in each case. Okay, you can find the wavelength of lambda 1, then lambda 2, and lambda 3. All three wavelengths you can calculate by applying suitable equations for Lyman series and Balmer series. Now, next question 10. In accordance with the Bose model, find the quantum number that characterizes the Earth's revolution around the Sun in an orbit of radius 1.5 into 10 power 11 meter with the orbital speed 3 into 10 power 4 meter per second. Mass of Earth is equal to 6 into 10 power 24 kilogram. Okay, we are asked to calculate the quantum number of Earth. So we can use this formula MVR, angular momentum. MVR is equal to NH by 2 pi. NH by 2 pi. So from this equation, you can find the value of N, the quantum number of Earth. Okay, so you can see the value will be very high in the order of around 10 power 74. A very high value you will get in this case. Okay, in the order of 10 power 74. Okay, then next question 11. Answer the following. Is the average angle of deflection of alpha particles by a thin gold foil predicted by Thomson's model much less, about the same, or much greater than that predicted by Rutherford's model? It will be almost same. And what is the reason? Because we have taken the average angle of deflection. As you have taken the average angle of deflection, you will get almost same. Then part B is the probability of backward scattering, that is scattering of alpha particles at angles greater than 90 degree, predicted by Thomson's model much less, about the same, or much greater than that predicted by Rutherford's model. Okay, so here the answer is much less. So what is the reason? In Rutherford model, you can see the entire positive charge and the mass are concentrated in a small region which we call the nucleus. But in Thomson's model, there is no such nucleus. Therefore, the possibility of backward scattering will be much less in the case of Thomson's model. Okay. Then part C, keeping other factors fixed, it is found experimentally that for small thickness T, the number of alpha particles scattered at moderate angles is proportional to T. What clue does this linear dependence on T provide? Okay, so the thickness increases. The possibility of collision is high. Okay, so when more atoms are present, when the thickness increases, so we can say the probability of getting the collision is high rather than just passing through the foil. So that is the reason there is a linear relation with the thickness T. Okay. Then next, part D. In which model is it completely wrong to ignore multiple scattering for the calculation of average angle of scattering of alpha particles by a thin foil? The possibility of multiple scattering is more in the case of Thomson's model. So what is the reason we need to consider the multiple scattering there? Because according to Thomson's model, you can see the positive charges are distributed in the atom. So an alpha particle which is deflected from a particular positive charge again have an interaction with another positive charge, so that you will get multiple scattering from a single atom. But in the case of Rutherford model, the entire positive charge is concentrated in the nucleus, so the possibility of multiple scattering is comparatively less. Okay, so in Thomson's model, we expect the possibility of multiple scattering. Then next question 12. Okay, the gravitational attraction between electron and proton in hydrogen atom is weaker than the Coulomb attraction by a factor about 10 power minus 40. 10 power minus 40. Okay, so now you are asked to estimate the radius of the first Bohr orbit of hydrogen atom if the electron and proton were bound by gravitational attraction. So instead of electrostatic attraction, which governs the orbit and other aspects of atom, you are asked to assume it is gravitational force that binds the electron with the nucleus. In taking that aspect, you are asked to calculate the radius of the electron. Now, okay, we have the formula Rn is equal to n square h square epsilon naught divided by pi m e square. Now, divide and multiply this equation by 4 pi. You will get Rn is equal to, you can write the equation like this, n by m. Rn is equal to n square by m. Okay, n square by m into h square divided by 4 pi square into 4 pi epsilon naught divided by e square. 4 pi epsilon naught divided by e square. Now, in this equation, here you can see the term 4 pi epsilon naught divided by e square. Okay, so that term actually we get from electrostatic force. F is equal to 1 by 4 pi epsilon naught q1 q2 by r square. So from there we will get. So now in this formula, the 4 pi epsilon naught, 4 pi epsilon naught divided by e square. Actually in the force formula it is e square divided by 4 pi epsilon naught. q1 q2 divided by 4 pi epsilon can be replaced by 1 divided by, we have to take gravitational force, so G M E M. G M E M. This constant should be replaced by 1 divided by G M E M. Then you find the value, okay, substituting, replacing that constant, then you find the value of R. Okay, so you can see when you find the value of r, then okay, you can take n is equal to 1 and find the Bohr orbit. So you can see there the value of r1 will be in the order of 10 power 29 meters, which is slightly greater than the estimated size of universe. So imagine the situation: if gravitational force binds the nucleus and the electron, then size of the first orbit in an atom will be even more than the size of the universe. Okay, so that we can conclude that uh, the gravitational force has no much role in binding the electron with the nucleus. Okay, and it is governed by, of course, the electrostatic force only. Okay, now next question 13. Obtain an expression for the frequency of radiation emitted when a hydrogen atom d excites from a level n is n to level n minus 1. Okay, you're asked to obtain an expression for frequency of radiation. Okay, so we can start from the energy formula, that energy difference E is equal to h nu is equal to h nu is equal to m e power 4 over 8 epsilon naught h epsilon naught square h square into 1 by nf square minus 1 by ni square, 1 by ni square. Okay, from that formula we can cross multiply the equation and find the value of nu. Nu is equal to m e power 4 over 8 epsilon naught square h cube into the final level is n minus 1. So 1 divided by n minus 1 the whole square minus 1 by n square. Okay, now we have to take LCM there, then simplify. When you simplify, you will get the answer. Nu is equal to m e power 4 divided by 8 epsilon naught square h cube into, in numerator you will get 2n minus 1 divided by denominator, you have taken LCM there, so n square into n minus 1 the whole square. So this is the answer you get for frequency of the radiation. Now come to the second part of the question. For large n, show that this frequency equals the classical frequency of revolution of the electron in the orbit. Okay, so first of all you are asked to take n is very big, value of n is very big. If value of n is very big, means that 2n minus 1 can approximate to 2n, and n minus 1 also you can approximate to n for large value of n. So accordingly, what happens? The frequency formula becomes nu is equal to m e power 4 divided by 8 epsilon naught square h cube into, in only denominator if you will get 1, n cube, and numerator 1, 2 will remain there into 2. This is the frequency for a large value of n. Now You take the equation for the speed of electron in the nth orbit. Okay, we are going to apply Bohr atom model now. So you will get a Vn is equal to, the formula is E square divided by 2 epsilon naught NH, and Rn again Bohr atom model. So N square H square epsilon naught divided by pi m E square divided by pi m E square. Now we can have time period T is equal to 2 pi Rn divided by Vn, or frequency is equal to 1 by T is equal to Vn divided by 2 pi Rn. Now in this formula, you substitute the values of Vn and Rn. Then simplify. You can see you will get an answer which is same as the value of mu given there. So hence you can prove that both the frequencies are equal. The question you have to note and you have to study properly. Okay. Then next question 40. Okay. Go through the question. Then see how to find the answer. Part A, construct a quantity with the dimensions of length from the fundamental constants E, M, E, and C. Determine the numerical value. Okay, when we go for such a calculation, you can consider an energy consideration. You can take, E is equal to mc square, which is equal to, take the case of potential energy here. The potential energy is equal to, what is that, 1 by 4 pi epsilon naught Q1 Q2. For hydrogen atom, Q1 Q2 is E square by R, potential energy. Now cross multiply this equation and find the value of R. Okay, so when you cross multiply that equation, you will get a quantity in the dimensions of length and find the value of R, and you can see the value will be in the order of 10 power minus 15 meter, which is much greater than the much less than the Bohr orbit. Okay, now see the part B. Again you are asked to calculate, okay, the same length with the help of some other quantities like M, H, E, etc. So when you use that formula here, again I have given the formula in question 12. That formula we can use, which we have used in question 12. We have a radius formula there. Okay, like R is equal to n square by m, then h by 2 pi the whole square into 4 pi epsilon naught divided by E square. So this is what given by Bohr. Okay, actually we have used that Rn formula. That's it. It is nothing different. Only we will multiply here, multiply and divide by 4 pi. That's only difference. Okay. Now substitute the values. Okay, and you find the value. You will get the value of Rn in the order of 10 power minus 10 meter, which is almost same as Bohr atom model. Okay, so that really, so you will get a reliable value of R when we follow the Bohr atom model. Okay, now Question 15. The total energy of electron in the first excited state of hydrogen is 3.4 electron volt. What is the kinetic energy? Kinetic energy will be plus 3.4 electron volt. Kinetic energy is the positive of total energy, the same concept we can apply. And what is the potential energy? Potential energy will be its double and negative, so 6.8 electron volt. Then which of these answers above would change if the choice of the zero of potential energy is changed? Okay, potential energy depends on reference point, you know. Okay, for gravitational potential and all, we took the reference point at infinity. Otherwise, if we have potential energy mgh, the h is measured from a reference height. So according to the reference, you can see potential energy will change. And the potential energy changes, total energy changes. Okay. But you know, kinetic energy is independent of such a reference point, depends on mass and velocity only. So wherever you consider the zero potential, there is no change in kinetic energy, but potential energy and total energy will change. Now, next question 60. If the Bose quantization postulate, okay, it's about angular momentum ns by 2 pi, is a basic law of nature, it should be equally valid for the case of planetary motion also. Why then do we never speak of quantization of orbits of planets around the sun? Okay, if you can apply quantization principle for the distribution of electron around the nucleus, why can't you apply the quantization principle for the distribution of planets around the sun? That is the question. Okay, so in question 10, we have calculated an approximate quantum number of Earth, okay, around the sun, and you got the answer in the order of 10 power 74. Okay, so we can approximate 70 or 74. Whatever. When in such a situation, you see the size of the value 10 power 74. Okay, it is a very huge value, even beyond our imagination. If that is the case, then is it possible to say n equal to 1, n equal to 2, n equal to 3 like that? In a number 10 power 74, is there any relevance to say the value n equal to 1, n equal to 2, n equal to 3, etc.? No, not at all, because this value is that much of big in size. So we can say, instead of having 1, 2, 3 like that distribution, we can say this distribution will be continuous. A discrete distribution you cannot observe there because of the huge size of this number. We can say the distribution becomes continuous. A continuous distribution will be there. Okay, the distribution becomes continuous. So therefore, being a continuous distribution, it's not possible to apply the principles of Bohr quantization in the case of planetary distributions. Now, next question 17. Obtain the first Bose radius and the ground state energy of muonic hydrogen atom. Okay, it is given what is meant by muonic hydrogen atom. An atom in which a negatively charged muon of mass about 207 times mass of electron orbits around a proton. Okay. So first of all, the Rn formula you can see there. In Rn formula, just here we have the formula for Rn. What kind of relation between Rn and mass? You can see Rn is inversely proportional to M. So that's a concept we are going to take here. So we have radius of the orbit is inversely proportional to mass. If that is the case, then we have radius of muonic hydrogen divided by radius of electron is equal to the ratio Me by Me, inverse relation. And that ratio is given around 1 divided by 207. Therefore, R mu you can calculate. R mu is equal to R E divided by 207, and R E 0.53 angstrom 10 power minus 10 divided by 207. Okay, so you will get the radius of the muonic hydrogen. The next energy formula you have to see. The energy formula is m e power 4 like that. So we have energy and mass having the relation E proportional to M. So accordingly you have E mu divided by energy of electron is equal to M mu over M E, that it's around 207 according to the question. So from there you can find the value of energy E mu. Okay, so you will get a E mu is equal to 207 times energy of electron. E mu is equal to 207 times, or E mu is equal to 207 into E. And energy, energy is equal to minus 13.6. So this is equal to 207. So you will get E mu is equal to 207 times energy of electron. That is equal to 207 into minus 13.6 electron volt. So you will get the answer for energy of muonic hydrogen. Okay, so that's all the problems of this chapter. Thank you.